Planet X's latest update. Astronomers discover a new class of scary black holes in the Milky Way. This report is from an anonymous astronaut. Some black holes are small. Some black holes are giant. But oddly enough, in the cosmic fight between innocent passing stars and voracious black holes, scientists have never found a mid-sized black hole. Until now. The star cluster 47 Tucani, located about 13,000 to 16,000 light years from Earth, is a dense ball of stars. Hundreds of thousands of stars compacted into a 120 light-year span give off gamma rays and X-rays and more energetic events. But to date, no black holes had been found there. The center seemed ripe for opportunities to find one, but a lack of tidal disruption events and a jumble of stars hard to sift through obscured finding any lurking black holes there. The Harvard-Smithsonian Center for Astrophysics turned to two tactics to find the black hole instead. First, they observed the motion of the stars in aggregate and compared the rotation rate to what would happen if a black hole were present. Secondly, they observed the position of pulsars in the globular cluster. The research was published Tuesday in Nature. Black holes are the densest objects in the universe. But neutron stars, which include pulsars, are a close second, as both can result from similar events in which a giant star goes supernova and its dense stellar core collapses, though a few other mechanisms can create black holes. If the pulsars were the biggest objects in the globular cluster, they'd be nearer to the core and act as a chief gravitational attractor. But instead, pulsars are scattered across the cluster rather than congregating in the center of the cluster. This all suggests that a black hole of 2,200 solar masses is lying at the center of 47 Tucani. Until now, though, astronomers have typically only found black holes of below 100 solar masses or above 10,000, the latter of which are the behemoths that power galaxies. These intermediate mass black holes are believed to be seeds of supermassive black holes. As black holes feast, they gain mass. The intermediate mass black holes may form from several stars in a dense cluster collapsing, with the resulting black holes merging and creating a bigger black hole. They could also be black holes that have accumulated mass over time. And indeed, 47 Tucani is 12 billion years old, giving plenty of time to slurp up matter. There is also a scenario under which, shortly after the Big Bang, certain areas of the expanding universe were so dense they formed black holes shortly after the event. Finding more mid-range black holes can be hard. Black holes, especially larger ones, typically clean their general area of debris. But if an unfortunate star happens to cross paths with one, the resulting event could be detected by astronomers, allowing them to see an intermediate mass black hole in action. According to our education website, nearly all black holes come in one of two sizes: stellar mass black holes that weigh up to a few dozen times the mass of our Sun, or supermassive black holes ranging from 1 million to several billion times the Sun's mass. Astronomers believe that medium-sized black holes between these two extremes exist, but evidence has been hard to come by, with roughly a half-dozen candidates described so far. A team led by astronomers at the University of Maryland and NASA's Goddard Space Flight Center has found evidence for a new intermediate mass black hole about 5,000 times the mass of the Sun. The discovery adds one more candidate to the list of potential medium-sized black holes, while strengthening the case that these objects do exist. The team reported its findings in the September 21st, 2015 online edition of Astrophysical Journal Letters. The result follows up on a similar finding by some of the same scientists, using the same technique, published in August 2014. While the previous study accurately measured a black hole weighing 400 times the mass of the Sun using data from NASA's Rossi X-ray Timing Explorer satellite, the current study used data from the European Space Agency's XMM Newton satellite. This result provides support to the idea that black holes exist on all size scales. When you describe something for the first time, there is always some doubt, said lead author here at Pasham, a postdoctoral associate of the Joint Space Science Institute, a research partnership between UM's departments of astronomy and physics and NASA Goddard. Identifying a second candidate with a different instrument puts weight behind both findings and gives us confidence in our technique. The new intermediate mass black hole candidate, known as NGC 1313X1, is classified as an ultraluminous X-ray source, and as such is among the brightest X-ray sources in the nearby universe. It has proven hard to explain exactly why ultraluminous X-ray sources are so bright. However, some astronomers suspect that they are intermediate mass black holes actively drawing in matter, producing massive amounts of friction and X-ray radiation in the process. Against this backdrop of haphazard X-ray fireworks created by NGC 1313X1, Pasham and his colleagues identified repeating flares, each flashing at an unusually steady frequency. One flashed about 27.6 times per minute and the other about 17.4 times per minute. Comparing these two rates yields a nearly perfect 3:2 ratio. Pasham and his colleagues also found this 3:2 ratio in M80-X1, the black hole they identified in August 2014. Although the overall frequency of flashing was much higher in M80-X1. Although astronomers are not yet sure what causes these steady flashes, the presence of a clockwork 3:2 ratio appears to be a common feature of stellar mass black holes and possibly intermediate mass black holes as well. The flashes are most likely caused by activity close to the black hole, where extreme gravity keeps all surrounding matter on a very tight leash, Pasham said. The 3:2 ratios can also provide an accurate measure of a black hole's mass. Smaller black holes will flash at a higher frequency, while larger black holes will flash less often. To make an analogy with acoustic instruments, if we imagine that stellar mass black holes are the violin and supermassive black holes are the double bass, then intermediate mass black holes are the violoncello, said author Francesco Timsi, an assistant research scientist in UM's Department of Astronomy who has a joint appointment at NASA Goddard via the Center for Research and Exploration in Space Science and Technology. Pasham and Tumsi hope that identifying ultraluminous X-ray sources that exhibit the key 3:1 to flashing ratio will yield many more intermediate mass black hole candidates in the near future. Our method is purely empirical. It's not reliant on models. That's why it's so strong, Pasham explained. We don't know what causes these oscillations, but they appear to be reliable, at least in stellar mass black holes. NASA plans to launch a new X-ray telescope, the Neutron Star Interior Composition Explorer, NISA, in 2016. Pasham has already identified several potential intermediate mass black hole candidates that he hopes to explore with NISA. Observing time is at a premium, so you need to build a case with an established method and a list of candidates the method can apply to, Pasham explained. With this result, we are in a good position to move forward and make more exciting discoveries.